Yeah. One second. No, it was my fault. It's okay. I was checking. Okay. So, sorry for making you wait. So the last speaker of this morning's session is Aaron Wootton, coming from the University of Portland. So Aaron, thank you.
Thank you very much. Thank you to Anesta and Rabina for organising. It's wonderful to be here again. So I understand I'm standing in between us and lunch, so I'll try and be quick. This is joint work with one of my colleagues, Valerie Peterson, and an old student of mine, Jacob Russell. It was work from some time ago, but I haven't really spoken about it much before, so this seemed like a nice venue to do so. So we don't really need the overview. So before I talk about the main goal, so just some terminology. I don't know if this is standard terminology or not. So I'm going to say a subgroup H of a group G is finitely maximal if there's no supergroup that contains it with finite index. Okay. So the underlying question behind this talk is the following. So for a compact oriented surface S of genus 2 or higher, can we determine all finitely maximal actions of each cyclic group, CP of prime over P, in the full group of orientation preserving homeomorphisms? Okay, so can I find all cyclic prime subgroups so that as soon as I add any other automorphism to this, it generates an infinite subgroup of the homeomorphisms? Okay, so what's this strange looking picture here? This is going to be a sort of running theme. I couldn't figure out how to sketch this on some nice application. I'm sure there is now. But why did I choose this particular example? Well, I'm very much about visuals, and anyone who wants to can recreate this surface. That's exactly what this surface is. So this looks like it's a 5-volt surface, right? It's actually a genus 4 surface because I can open out, I can't do this, but I can open out one of the holes, and I actually end up with 4 different holes here. But the reason I've represented it in this particular way is because you can see 2 distinct actions here, right? You have a cyclic 5 action which rotates those holes, okay? And then if you pierce through one of the holes and then directly through sort of a leg on the other side, you have a cyclic 2 action. So in this particular instance, we have these 2 different cyclic groups that generate a dihedral group between them, so neither of these are finitely maximal. Okay, so why do we care about this thing? Well, from my own point of view, I like solving little problems like this. So it's interesting in its own right, but there are some other applications as well. So from the geometric point of view, there's a 1-1 correspondence with isolated strata in the branch locus of moduli space with these objects. And then from an algebraic point of view, there's also a 1-1 correspondence with finite subgroups of the mapping class group, or finite cyclic prime subgroups of the mapping class group, which are themselves finitely maximal. So there are some applications outside of it being interesting in its own right. Okay, so there's also, I'm certainly not the first person to consider this and related problems. There are lots of people who have. I've omitted authors because I've run into this problem sometimes where you quote some people and then someone in the back says, "Oi, what about me?" I did that as well. So it's just easier to omit everyone. There are significant or complete results known for small primes, significant or complete results known for small genus, so 100 or less, and then for special types of families as well. So for example, unramified actions are never finitely maximal. They always are contained in some supergroup, finite supergroup. And superelliptic actions, this is where the quotient has genus 0. Quite a lot is known about these as well. So as a caveat, as I said, this was a project from about 10 years ago. I've not stayed on top of this, so there could well be plenty more results beyond this. So I apologize if I'm not quoting anyone there. Okay, so now let's start getting to the meat of the talk. So some preliminaries first. In fact, most of the talk is preliminaries, and I'll just tell you what we found. So I usually describe actions via signatures. So in this case, since we're dealing with cyclic prime subgroups, signatures are relatively easy to describe. So we say, so for the rest of the talk, P is going to denote a prime as a compact oriented surface of genus 2 or higher, and CP is a cyclic group acting on this, just so I don't have to say that every single time. So we say that CP has signature H, semicolon, and then P r times. If the following are true, the quotient space X mod CP has genus H, and CP has our fixed points. So this is how we're going to describe these actions. And so for convenience, as I said, we already know everything about unramified actions, and so I'm going to assume that I have a certain number of fixed points. R is greater or equal to 0. R is strictly greater than 0. And as I also said, pretty much complete results are known for all small primes as well. So I'm going to assume P is greater or equal to 5. Though most of what I talk about hold in both of these cases, it just makes some of the technical details a little easier to follow. Okay, so going back to my first example here, I'm ignoring the cyclic 2, but I can derive the signature for this particular action. So again, I have my surface like this. I have my axes piercing through the surface. There are 4 fixed points, so that gives me 4 of these number 5s at the end of the signature. And then how do I get the quotient genus? Well, the way to think about this, right, is this cyclic 5 action identifies all of these holes. And so that if I open this out, I'm just going to end up with no holes whatsoever. So I'm going to end up with a genus 0 quotient. And so in this particular case, the corresponding signature for this action is 0 and then 4 5s. Okay, so that's how we're going to describe actions. So now the question is, how do we determine whether a given action exists with a certain signature? So I'm going to talk a little bit about local and global behavior in order to come up or to describe the criteria for testing whether or not an action exists with a particular signature. So let's suppose we have this group acting, and let's take a generator of that group, and let P1 through PR denote the fixed point list on top of the surface. Okay. Well, at any point, this is going to act like rotation through some primitive pth root of unity. So if I fix this x and I fix zeta, a primitive pth root of unity, then the rotational constant of a fixed point is defined to be the unique exponent of that primitive root of unity. So it looks like that rotation close to that point. Okay? And so from this, I define something called a generating vector. So the generating vector, now this does depend on this choice of zeta. It also depends upon, of course, this x. And it depends upon the ordering I've chosen here, right? Okay? But the generating vector is simply this list of powers of the generator of CPX raised to the power given by the rotational constant. Okay? It looks more complicated than it is. So again, if I go back to my cheesy example here, we have these 4 fixed points, right? My axes going through. Okay? Now, if I choose x to be the generator, which rotates by e to the 2 pi I over 5, so it rotates exactly 1/5 of the way through, when I'm looking down at this, right, in a counterclockwise direction, then my top point here and this point here, when it pierces through the bottom, those are going to be rotation through just center, and then when I'm looking up, right, it's going to be clockwise instead, and so my second two are going to be the local behavior is going to look like this, which is just the same as that, and so in this case, for this particular example that I have here, corresponding generating vector for this is x to the fourth, x to the fourth, written in the order that they have. This is unique up to permutation of these things. Okay, so there's a second property we need as well, which is a more global property. So that is the Riemann-Hurwitz formula. I think pretty much everyone here is probably familiar with this, but let me just quickly go over this idea because it'll be important later. So if you have a function, if you have a map between two Riemann surfaces of degree n, then of course the Riemann-Hurwitz formula holds. That is, if you have the set of ramification points in the original surface S. These are the points where the local behavior is some power map of Z. And for a given pi, if we let e to the pi denote the ramification index, then the standard formula, this is the general formula, not to our particular case, I'm just going over this. Then the standard formula for the Riemann-Hurwitz formula, or one of the representations of the Riemann-Hurwitz formula is given by this. And this, of course, restricts to our case, right? Because we have our surface on which our group is acting, and then the corresponding quotient surface, so it's a quotient out by a cyclic prime group, giving us some form of, the point here is some form of numerical relationship between the genuses of the corresponding surfaces and then the orders of the ramification points. So we already know what the quotient genus is here. We showed that it was 0, but you can verify this, of course, just going through the Riemann-Hurwitz formula. You have these 4 fixed points, each of degree 5, and so we can just go through and we can algebraically solve for this genus here. There's nothing special going on there. As I said, we already calculated this genus, but I just wanted to show Riemann-Hurwitz formula gives this. Okay, so putting these two things together, we can state a result which allows us to determine when an action exists with a particular signature. So we have the following theorem. So a given cyclic group acts on S of genus sigma with a given signature and generating vector given by this, if and only if the following two results hold. First of all, the first result is simply the Riemann-Hurwitz formula. And then the second result, and this is really the main idea here, is that this sum of the AIs have to be congruent to 0 mod P. Okay? So, okay, there's lots going on here, right? But the main point is finding actions is roughly equivalent to finding generating vectors plus some additional numerical condition. Okay? So remember, I mean, at the moment I'm just talking about CP actions. Ultimately, we want to be able to talk about when these extend or not. Well, the way we're going to determine that is we're going to look at conditions on generating vectors which either guarantee they do extend or show that they don't extend. Okay? Okay, a quick observation. Doing okay? No? 5 minutes apparently. Okay, so once again, that numerical condition comes from the Riemann-Hurwitz formula. And the nice thing about this is we can manipulate this, and it actually tells us every possible signature in a given genus with which a cyclic group of prime order can act. So specifically, if you have two different signatures, well, we can just set them equal to each other, right? Do a little bit of algebraic gymnastics, and we get that if we have two distinct signatures acting on the same genus for the same cyclic prime subgroup, then the difference in the branch points has to be a multiple of P, and the difference in the genera, the quotient genera, have to be a multiple of p minus 1 over 2. Okay? So in particular, it gives us this complete list of possible signatures, right? Every possible signature of a cyclic prime action. Once you've found one, every other one can be recovered just by subtracting off genus and adding fixed points, or vice versa, subtracting off fixed points and adding genus. So we can trade genus for fixed points. But what's more important for my case is the following. Because here we can keep subtracting off multiples of p minus 1 over 2, that tells me that the smallest possible quotient genus for my surface appearing in this signature is going to be smaller than p minus 1 over 2. Okay, so it's going to be between 0 and p minus 1 over 2. And in fact, you can show that as genus increases, each of these possibilities appear an equal number of times. In fact, there's a sequence of every single one of these, or an infinite sequence of every single one of these. Okay, so let's return to our example again. So we've already seen that there is at least one example of a genus 4, of a cyclic 5 action in genus 4. Okay, but I can actually write down now all of the possible generating vectors, right? So the generating vectors, what are we simply asking? We're asking that the Riemann-Herbert's formula is satisfied. We already know that. We've already tested this. And then we need the sum of these exponents to just be congruent to 0 mod p. So if I write down all the possibilities, then of course up to permutation of these things, these are the only possible ones. Okay, so of course there's plenty here. Each of these represents some form of action, so the obvious question is, when are these actions equivalent? And by equivalent, when are they topologically equivalent, since we're considering groups of automorphisms or homeomorphisms. Two generating vectors define equivalent actions if and only if they differ by a permutation of the AI and or an automorphism of the cyclic group CP. So once again, returning to our example here, so we have these 7 different generating vectors, and we can go through, and there are actually just 3 of these up to equivalence. So the first one is this, because notice if I apply an automorphism here, then this one is going to be equivalent, well, of course it's equivalent to this, but it's also going to be equivalent to this one here if I send x to x squared, so that eliminates those. Next one, if I take this generating vector here, and I apply either the automorphism x goes to x squared, x goes to x cubed, or x goes to x to the 4th, then I get these remaining 3, so that eliminates those. And then finally, this last one is, well, equivalent to the last one there. So, up to topological equivalence, there are exactly 3 different cyclic 5 actions on a genus 5 surface.
But some of the exponents is not divisible by 5?
Sorry?
Some of the exponents is not divisible by 5 in the second?
Did I, let's see. Oh crap, something's going wrong with this one, right? yeah. I think that must be a paste issue. Yeah, just ignore that one. I was cutting and pasting between slides, and I'm assuming some power messed up there. Well, that one's fine, the one at the end, right? So I think I screwed something up there. So that should be 1, 2, 3, 4.
1, 2, 3, 4.
Yeah, okay, all right. Sorry, I apologize. I finished this off under a lot of jet lag. So, okay, quickly back to the original question to tie it all up. So remember, the original question was, can we describe all finitely maximal actions of each cyclic group of prime order P in the full group of homeomorphisms? Well, finding CP actions is equivalent to finding generating vectors. That was the purpose of the last sort of 10-15 minutes. Okay? So in order to answer this question, we need to determine conditions on generating vectors, which determine when they define maximal actions, or equivalently when they don't define maximal actions. Okay? So once again, returning back to our example, okay, in this case we have the following generating vector, okay? And there's sort of a reason the generating vector appears as it does, right? Because the existence of this cyclic 2 action moves these two fixed points down to those fixed points as well. So because these are finite, they're also going to be conformal, so it's going to preserve the angles there. And so what's the point of this? Well, the point is extra automorphisms, that is, if you are contained in some finite supergroup, extra automorphisms are going to guarantee some form of symmetry in the generating vector. In this case, we can see the symmetry directly, right? So the second thing we know is if there's a larger group of automorphisms, then we're going to have some form of Riemann-Hurwitz relationship between the corresponding quotient spaces, okay? So the point being is that there's going to be some further numerical condition that's going to be applied, okay? So the point of these two slides is the following. If there's some finite supergroup, there's going to be some form of symmetry in the generating vector, and there's got to be some additional numerical condition that's guaranteed to be satisfied, okay? And if neither of those two things happen, then we have a chance that this thing is going to be finitely maximal. So with this in mind, the observations we made in the previous two slides actually generalize to the following, and that is, suppose we have a cyclic prime group acting on a surface, then it extends to the action of a dihedral group, if and only if we have a similar sort of thing going on with the generating vector, that is, each of the elements come in pairs, where you have x to the a and x to the minus a appearing an equal number of times, and then you have this strange numerical condition coming on, that is, their existence as your G and M with this property. Well, where are these coming from? These are just coming from the fact that we have to have some additional quotient surface and some additional branch points, and it's just giving that information there from the Riemann-Hurwitz formula between the map between those two surfaces. So going back to my original example, if I choose G equals 0 and M equals 2, we see that both of these generating vectors are generating vectors which extend to an action of the dihedral group of order 5. So both of those C5 actions extend. Ignore that last line because it's wrong. Okay, now the reason I looked at the dihedral example because I was able to really illustrate this with my cheesy example up here. Okay, but this sort of idea holds to other groups as well. That is, you can come up with similar sorts of theorems for other possible extensions. So, for example, you can come up with a similar theorem for when CP extends to a cyclic group C2P. So in this case, once again, you have this sort of situation where in the generating vectors, you have pairs of elements pairing off, and then you have some form of tail at the end of other stuff. And then, again, we have sort of in this case, it's slightly more crazy, but some form of numerical condition that has to be satisfied. Okay? Again, the details aren't important here. What's important is we have some form of symmetry in the generating vector that has to be satisfied. We have some form of numerical condition that has to be satisfied. If we can show those two things hold, then the group definitely extends. And so in this case, again, for that last one, okay, if I choose G equals 0, K equals 2, and N equals 0, then I can write this generating vector in that form, right? I pair off these two, and then I have this tail at the end, so it matches this form, and then I've chosen my constants here, so it satisfies this corresponding equation. So in particular, I've shown that all three of them extend, so there are no finitely maximal ones. And I'm almost done. So, okay, so back to the original problem. How does this apply in general? Well, from this, it's relatively easy to show that there's an infinite sequence of genera for which CP will never be finitely maximal within that genera. Okay? So the basic idea is to show that it can be extended using one of these previous theorems. Okay? So let's assume that, if CP is finitely maximal, then the genus has to be less than p minus 3 over 2, and this is then going to allow me to construct this sequence. Okay? So I'm proving this is relatively straightforward. If H is bigger than this, so the quotient genus is bigger than this, well, any generating vector for CP can be written this way. So what do I mean by that? Well, a generating vector is simply a bunch of powers of x. I can move all of the pairs to the front. I can pair things off and move them off to the front. And then I'm going to be left with some tail here of individual powers which didn't get paired up. Okay? Now, there are only p minus 1 non-trivial powers of x, so the maximum number of things here is always going to be less than p minus 1. And so then I can choose a value of m, choose a value of g to satisfy the Riemann-Hurwitz formula, and this then guarantees extension to C2p. So if my cyclic group has genus p minus 3 over 2 or higher, then I'm guaranteed that it's always going to extend to an action of a cyclic group of order 2p. This is the thing I was thinking of. So what this tells me is there's an infinite sequence of genera for which CP is never finitely maximal. So in particular, what do I know? This is what I pointed out earlier on. I'm always guaranteed the smallest genus, the smallest quotient genus is always going to be less than p minus 1 over 2. It's easy to construct a sequence of genera where the quotient genus is always p minus 3 over 2. And so, since we know all possible h's, which are p minus 3 over 2 or higher, all of those extend to a C2p by a previous result. Anything lying within this sequence is always going to extend. So this example here gives me this infinite sequence of genera for which the cyclic prime group is never finitely maximal in the group of homeomorphisms. And one last thing I want to say. Okay, so this talks about non-maximal actions. We've constructed this infinite sequence of non-finitely maximal. So what about finitely maximal? Do they always occur, and how often do they occur? Well, we have this result here, which says, okay, well, for sufficiently large genus, provided the smallest h of a CP is not p minus 3 over 2, because we've shown that in that case it always extends, then there always exists finitely maximal CP actions on the surface of genus sigma. And in fact, for p greater or equal to 7, provided the genus is bigger than this quadratic, then the number of such actions up to equivalence is bounded below by a linear function in the genus. So in fact, not only are there finitely maximal actions, most of the time, there's a heck of a lot of them, in fact. If it's good enough for Fermat, it's good enough for me. Okay, so, I mean, the basic idea, right, we have this symmetric condition on the generating vector, and we have this numerical condition. You can essentially construct a linear number of generating vectors which fail to extend to any possible order. That's sort of the big idea, but it took quite a few pages to prove this thing. And no one wants to see that when they all want to go for lunch. Okay, thank you.
Questions, comments? Yeah, we're starting.
Yeah, I know.
So, okay, since we are a bit late, so let's thank Aaron. About lunch.
Yes.
You can go wherever you want to have lunch, but there is at least one controlled option. If you want to join this option, you are more than welcome, but you are free to. I mean, we have a reservation there, but they know that maybe not everybody is coming there, so there's no problem about that. Maybe there's and second thing, there's a room here called the Blue Room. The first door here, which is also in use of this meeting. It's also ours. So you can enter there to discuss with some colleague. There's a whiteboard there. And you can leave whatever you want to leave because they will lock this blue room. Not this one, but this blue room will be locked.
Can be locked.
So if you want to leave whatever. Pues luego te enseño si converjo en diferentes tipos de problemas, pero luego te explico qué es lo que hay que hacer.
Vale. Claro, yo entiendo cómo venir sin problemas. Si necesitas...
Si te necesito, de todas formas, luego igual pillo.
Si no me necesitas, seguramente también venga, pero...
Luego igual pillo más que también le dije que igual le liaba.
¿Es tuyo el portátil?
Este es de... ¿Por qué?
El resto, yo entonces me voy bajando y yendo ya con algunos, ya es casi la hora, y luego, ¿no?
Sí. ¿Puedes decirle a alguien que suban a cerrar? Voy a meter mis cosas
Me
también.
ha gustado y está aquí, pero hay alguien que...
Alguien la podrá llamar abajo.
Ya que se van a cerrar, nadie ha dejado nada ahí, un minuto.
Bueno, yo sí que voy a meter esto.
Vale, lo digo.
¿Qué hacéis? ¿Qué desgraciado? ¿Este teclado?
El teclado, no se escribe bien. Es que esta marca de portátiles, estoy pensando en comprarme un portátil nuevo.
Ah, ya, menos mal que me das explicación a tu strange behavior.
Y este Dynabook me gusta como marca.
Ah, sí, no conocía esta.
Porque esta es la antigua Toshiba.
Ah, que Toshiba ya no existe.
Toshiba es Dynabook ahora.
Oye, que con mucho más.
¿Ves? Toshiba converge a Dynabook.
Ah, sí, yo tuve algún Toshiba que no fue mal.
Yo tuve un Toshiba que fue muy bien. Voy a sacar una foto para
que lo puedas mover.
Claro, es...
Si les suban el proyector que se joden, ¿no? O no, como lo guardo.
¿Eh? ¿Qué he dicho?
Os dejo todos los cables.
Y la cámara.
Hay medidas, la cámara la cojo.
Y metemos las bolsitas de la gente que lo hace.
para abajo, me dice, bueno, está quedando, digo, bueno, vale, ya voy a girar con la que también no pasa nada.
Sí, porque lo he dicho yo antes y digo, parece que no.
Sí,